Okay, so maybe we get started. Yeah, it's time. Yeah. Okay, so good morning, everyone. It's my pleasure to introduce Ilaria Maccari. She's an SNF fellow, SNSF postdoctoral fellow at ETH. But before getting where she is now, she did her PhD in Sapienza University. She finished in 2018, and we basically just missed each other by a few months because I went there to do my first postdoc, and she went to do her first postdoc to Stockholm until the 2023, the end of 2023, where she went to do postdoc to PSI in Switzerland with Aline Ramirez for a few months. And then last year, around April or May, she moved to ETH, where she's now with Manfred Sigrist group. And today she's gonna talk about the role of topological phase fluctuations in two-dimensional and multi-component superconductors. So Ilaria, the floor is yours.
Thank you, Maria, for the nice introduction, and thank you for being here. I know that it will be another seminar today, so I hope to just warming you up without getting you asleep. So maybe I will be here so I take track of the time. So yes, as Maria said, I'm going to talk a bit of what I've been working on in these years, which can be summarized by this title. Before starting, I would like to do a brief introduction, just to be sure that we are all on the same page and to introduce you my, let's say, theoretical framework. So as you know, let's say the main protagonist of this talk is, of course, superconductivity, superconductors in metal form. So all this beautiful phenomenology, which goes from zero resistance, Meissner effect, and magnetic flux quantization, can be explained, as you know, in terms of the formation and condensation of Cooper pairs. So essentially, we can describe all this phenomenology within the Gisborne-Landau theory by introducing this complex order parameter, which accounts for the formation of Cooper pairs via the amplitude field and for the condensation via the phase. So when I will speak about superconducting phase fluctuation, I will refer to this field here. So within this Gisborne-Landau theory, then the picture is more or less the following. At very high temperature, we don't have bounded state, so we have zero pair density and free electrons. Below a certain temperature, this electron starts to bind into pairs, and the free energy landscape change in this way. But this is not enough to have a superconducting state because Cooper pairs need to condense in a single quantum mechanical state. And to break this symmetry here associated with the Goldstone mode, so to this degree of freedom associated to the phase. And when they do so, we have a superconducting state, essentially. So far, so good. So what I will talk about today, as I already mentioned, is the role of phase fluctuations. Yes, as I already said, this leads to a spontaneous breaking of the U1 gauge symmetry. And this phase field can have both smooth deformation of the phase, but also topological defect. So these topological objects are, in this case, vortices, and are objects that cannot be smoothly deformed in an ordered state. This physics, the physics of superconducting phase fluctuations, is important in those systems where the energy scale associated with the quasi-particle excitation, so associated with the amplitude, if you want, of this order parameter, is larger than the energy associated to the phase fluctuation, so to the phase rigidity, which is the superfluid stiffness. This is, of course, the case of two-dimensional superconducting systems, where actually the whole superconducting transition it can be described in terms of the unbinding of these topological objects that are vortices and antivortices. As you know, indeed, in two dimensions, we cannot have an order parameter, this delta, that becomes finite from zero at any finite temperature because of Mermin and Wagner. But we still have a superconducting state due to the fact that these Cooper pairs have a quasi-long range order in the phase, so the phase is rigid, despite allowing from smooth deformation of the phase. So this is the well-known BKT phase transition, as you know, so it's essentially governed by the unbinding of these vortices, which occurs at a critical temperature, where this superfluid stiffness, which is a physical observable, as we will see, drops to zero from a finite value. Okay, this kind of physics is getting more and more important, especially because of the new technological advances in the realization of very thin films, even monolayers. And I mean, here there are many experts working on this field, actually. And of course, all the realms of van der Waals heterostructures, where you can essentially use these monolayers as a building block for constructing and realizing new compounds. So in this talk, I will try to guide you on some of the questions we try to answer concerning the role of phase fluctuations in 2D superconductors. So the questions are of this kind. So how do vortices interact with disorder, which is always present in these kind of systems? Is a jump in the superfluid stiffness always a signature for a BKT phase transition? Or how does a two-dimensional Brikosov vortex lattice melt with temperature? These are just a selection of the questions we try to address, but for time, I mean, I just selected a few. And in the second part of my talk, I will instead introduce a completely new topic, which is the possibility of a completely new phase of matter driven by the proliferation of this topological object in multi-component superconductors. So let me start briefly with the first topic. I will be a bit fast, but you can be free to ask me questions later. So about the first question, how do vortices interact with disorder? So from the textbook picture, we know what we should expect in thin superconducting film. So the superfluid stiffness should follow in temperature a BCS-like trend due to some unbinding of quasi-particles. And once reaching the BKT critical line, one should observe a jump, because at that temperature, vortices start to unbind and the superfluidity drops suddenly to zero. Experimentally, it was observed something different. So these are quite old measurements, but also the more recent one often are of this kind, taken on niobio-nitride systems with different thickness. And as you can see, the deviation from the BCS trend appears in a small region, and also it doesn't show the expected jump at the critical line. It seems a more broadened transition. This was already thought to be due to the presence of disorder that produced this kind of smearing. But in these works, we realized that the real question to ask was which kind of disorder actually produced this smearing. Because in our study, that was done via Monte Carlo simulation on an effective model for the superconducting phase, we actually observed that so the blue curve is the clean case with no disorder, and the red and the green curves are for two realization of disorder with the same strength, one with spatial correlations and one without. So we realized that actually the key factor to have such a broadening in the transition was the presence of spatial correlations in the disorder. So the presence of an inhomogeneous superconducting system that induce an anomalous nucleation of vortices. This is the vortex density in those regions where the superfluid density is lower. This actually found confirmation very recently in a work done in collaboration with the group of Christoph Strank, where they observe a very sharp jump for the superfluid stiffness in the same materials of this measurement here. Why? The reason is that both the technique and the deposition method was such to obtain a sample that was more homogeneous. First of all, because here they use two coils, mutual inductance, so they require larger samples, and so they could have more inhomogeneous patches, essentially in the same thing. While here the system was very homogeneous, and as you can see, in this case, despite being disordered, the transition is sharp. So very quickly, the second question, is a jump in a superfluid stiffness always the signature of BKT physics? So this is another, let's say, research line we pursued in Rome, essentially, where we studied the anomalies observed in the 2D electron gas at the interface between two oxides. And what was observed, of course, this depends on the doping, but essentially the characteristic were a separation with respect to the expected trend between the vanishing of the resistivity and the onset of a superfluid response, and also an anomalous conductance here at 0 temperature. So this sharp jump was, I mean, one can think, okay, maybe it's just BKT physics, right? Because it's the unbinding, we know the story, and so on. But actually, if you look at the BKT critical line, you realize that this is nothing to do with the BKT physics. So in this case, the BKT is completely masked by the disorder, which is at the nanoscale. And this phenomenology can be explained in terms of an emergent so-called filamentary superconductivity, in the sense of a percolative transition where superconducting paddles in this very inhomogeneous system found at a certain temperature a percolating path that is very fragile, so the superfluid stiffness response is very low, and then it grows by many mechanisms. One of these is the proximity effect. The last question I want to just present to you, we try to address in these works, is about the melting of the two-dimensional Briggs-of vortex lattice that forms in thin superconducting films when you apply a perpendicular magnetic field. So why it is interesting? Well, because in 2D, actually this melting transition doesn't occur like in 3 dimensions, so via just one single step from a crystal to a liquid phase, but it can occur in 2 steps via an intermediate phase, which is called vortex exotic liquid phase. This phase is reached via 2 continuous phase transitions driven by topological defect, which are these locations in this case, and disclination in this other case. So essentially, these locations are such to destroy the translational order in the lattice while retaining an orientational order. So this exotic vortex liquid is a sort of liquid crystal. If I mean, there are is still ordered with respect to the orientation of the vortices. So what we did in this work was to characterize these 2 steps melting transition theoretically and experimentally via 2 methods. So looking both at the static properties, meaning essentially how the vortex lattice evolves in temperature, which tells us about the proliferation of the effect. So for instance, this is an example of measurement and Monte Carlo simulations in this intermediate state where you see the presence of these locations of this kind of defect, but still you can see from the structure factor that you have these 6 spots indicating that there is a 6-fold orientational order. We also characterized, of course, to be sure that to distinguish between a liquid phase and a solid state, we need to probe the dynamic to see how the system responds to some external forces. And we did it, I mean, via Monte Carlo, we look at essentially at the diffusion of the vortices via thermal energy. We track each vortex in time individually, and we could extract the mean square displacement, and from that, the diffusion coefficient as a function of the temperature. And that's very interesting because this is directly related to the linear resistivity of the system that can be accessed, of course, via transport. What we found is very cool because essentially we found that when you enter in the excitic phase, the system shows a deviation from the standard Arrhenius activated behavior following what is called the Vogel-Folker-Tammann law. It doesn't matter the name, it matters the fact that the diffusion becomes even more suppressed as a result of the presence of a very heterogeneous dynamics, which is very similar to the physics observed in so-called fragile glasses. So in the physics of fragile glasses, you actually really observe this kind of deviation. And the Arrhenius law is recovered when you go in the strong glasses regime. What was interesting on this study is that as a function of the magnetic field, we could observe that this excitic phase that was present at low field, as you can see also from this bit of the data, disappeared, recovering a completely Arrhenius activated behavior at a larger value of the magnetic field. And this result was very interesting because essentially it allows us to draw an Angel's plot, which is very typical very known in the community of people working on glasses, where you can essentially categorize glasses in terms of their fragility. So very fragile are very strongly dependent on temperature, viscosity very strongly dependent on the temperature, and strong not. And the cool thing is that in this case, this fragile to strong phase transition could be driven by a single knob, which is the magnetic field. While typically one needs to compare different materials to get such a plot. So here instead, we could really study the transition by looking at the variation in magnetic field. Okay, this was just an overview. I was fast, I know, but now we spend a bit more time on this last part, which is, I think, quite exciting. So the idea is, can we stabilize some kind of electron condensate that goes beyond the Cooper paradigm? What does it mean? So essentially, in the picture I showed you before, it seems like we cannot do much better than this. So there are electrons pairs up and they condense in a single quantum mechanical state. So how can we realize the condensate formed by more than 2 electrons? How can we go beyond this paradigm? So I will try to guide you through this. Starting from the main ingredient. So what we need is something more than just one component. So we need a superconductor that has multiple components. This can be realized in many ways. It can be the case of multi-band superconductors, single band with unconventional pairing, or even mixture of charged condensates. So on the right side, I will just guide you on a very simple example to show you the mechanism how these new phases can be stabilized. So here I just write the order parameter for 2 components for these 2 species of Cooper pairs, psi1 and psi2. So the second ingredient we need is a ground state that breaks multiple symmetries. So some kind of intercomponent interaction between the 2 that leads to not just the U1 symmetry that is broken spontaneously, but something else. One, again, a very simple example can be done by writing the free energy Gisborne-Landau simply for 2 components without assuming any direct coupling between the 2. and just assuming an interaction via the electromagnetic field. This is already enough because if you rewrite the free energy now in this way, you can see that you can point out which are the physical modes of the system. So the physical modes are two. There is a mode that is coupled to the electromagnetic field. So this is the superconducting mode. It's the one that gives you the Meissner effect once the phase becomes rigid. And a mode that is instead related to the phase difference, so to a counterflow of the two species of Cooper pairs, which is a superfluid mode. So in the ground state, the system will break, in this case, a total symmetry that is U1 cross U1. So this very simple example already fulfills the second condition. The third condition is the following. So we need something that destroys the coherence among Cooper pairs belonging to the same species while maintaining the coherence among pairs of pairs. So in this case, we will have something that is formed by 4 electrons rather than 2. So something that does something like that, exactly. So what can be? So in this context, again, the principal role is played by topological excitation of the phases, because in this case, we can have more kind of vortices, not just vortices in the individual components, but also composite vortices, where the phase of the two components wind around the same core. And this kind of composite vortices can be either co-direct, like in this case, or counter-direct, like in this other case. What is the key thing about this story? The key thing is that essentially these topological excitation affect differently the two sectors. In particular, if we imagine to start from a superconducting superfluid phase in this toy model, and we imagine that the first vortices proliferating are this one, which is plausible because they are the cheapest in energy since they are screened by the electromagnetic field. These vortices, as you can see, preserve the phase difference while destroying the phase sum of the two components. So we end up in a phase where the system is no longer superconducting, so we don't have a Meissner effect anymore, but there is still a residual superfluidity in the counterflow of the two components. So this is an example of fermion quadrupling condensate, because this state can be expressed essentially with this order parameter, which is a quadratic combination of these two bosonic fields, and then essentially 4 fermionic fields. Then, of course, these vortices can unbind, and we can come back in the normal metal phase. So to sum up, to summarize what I've just told you, when we have a multi-component superconductors with multiple broken symmetries in the ground state, vortices, topological excitations can stabilize as so-called vestigial phases higher order electron condensate. So this is the case, for instance, of fermion quadruplets. This can appear actually both above the superconducting critical temperature, and this is typically associated with the phase difference between the component, or below. So, and this is the case, maybe you have heard about it, of the charge-free superconducting state, where essentially the coherence now is in the phase sum, so the system is still superconducting, but the condensation is not of the pairs of the individual spaces, but it's pairs of pairs that condensed in a single quantum mechanical state. What about experimental realization? Well, recently we success to observe the first experimental signature of this phase in an iron-based superconductor. Let me present briefly the story to you. So this is the phase diagram that was assessed before our new experimental result, where you can see here is the doping. So this is iron barium arsenide doped with potassium. And you see that at the verge of the Lifshitz transition, it appears a dome where the superconducting state additionally breaks time reversal symmetry. This is due to the fact that the system essentially experienced in this range of doping a strong phase frustration between the three bands. So it goes from a situation at low doping, where the strongest repulsion is between the hole and the electron pocket, to a situation where the electron pocket has shrinked out, and the strongest repulsion now is between the two hole pockets. So in between, there is a regime where the three bands are frustrated. So they want to be, the phase in the three band want to be anti-aligned. So it's a situation very similar to the case of an Ising model with antiferromagnetic interaction on a triangular lattice. And the way the system managed to minimize the energy is to arrange the three phases in this Mercedes-Benz configuration, which has two possible realizations, two chiralities. And these two chiralities are one, the time reversal of the others. So when in the ground state, the system chooses one of the two, it spontaneously break the time reversal symmetry, so the zeta-2 time reversal symmetry. The free energy functional is this one, so it can be described by these Josephson frustrated terms. Essentially, so the idea was to check whether here there could be some splitting of the two phase transitions, so if the two occurs together or not. So these were the experimental observation. As you can see, one can identify a low temperature phase where the system has a Meissner, the magnetic response, this blue curve, the Meissner effect. The resistivity is zero. A high temperature phase where there is no anomaly in the specific heat, the system is resistive. But in between, as you can see, there is a third phase where one observes essentially an onset of the anomalies in the specific heat. The system is still resistive, and more importantly, one observes a spontaneous Nernst effect, meaning that the system has spontaneous magnetic field, signaling the spontaneous brokening of the time reversal symmetry. Yes?
So, in the phase diagram, what are the blue stars? Is this resistivity?
Yeah, this is TC.
Measured by
resistivity, yes. Exactly. And this is measured by muon spin at this level. Indeed, I don't have the picture, but the muon spin measurement confirmed also the time reversal symmetry is broken in this exact regime in temperature. So this picture was consistent with the idea that a third phase that we named quartic metal phase appeared between an S plus IS superconducting state and a metallic state. These measurements were also repeated at finite field, and this is the phase diagram as a function of the magnetic field and the temperature. Another important thing to notice is that we also observe a strong regime, quite large regime of superconducting fluctuations. Yesterday, actually, was released a new paper on the archive by the experimental group when they studied the pseudo-gap phase, which is also a key ingredient to confirm our picture, because you have preformed Cooper pairs that first develop order in the chiral order, and afterwards a superconducting order. There were other experimental measurements confirming these phases. I already mentioned muon spin, but also ultrasound measurement. Recently, the experimentalist collaborator managed to observe two peaks in the specific heat, confirmed also by my simulations. And it was observed the presence of metastable fractional vortices, which is also another indication that the picture seems correct. And even more recently, they observe fractionalization of these vortices by looking at the surface of this material, essentially. So the picture seems consistent overall. I have to say that from the theoretical point of view, this was not trivial to stabilize this phase. So if you take just the more standard, let's say, three-band Gisborne-Landau model, you don't find this phase at zero magnetic field. So we needed to introduce by hand another interaction between the component, which is a sort of drag dissipation and interaction. This is the simplified model, and as you can see in this simulation, you see that these are inverse critical temperature split, where when this coupling term is strong enough. Essentially, this term here is favoring the co-flow of the component. So of course, it favors the proliferation of co-directed vortices, and then it's easier to destroy the superconducting sector with respect to the chiral sector. But a microscopic derivation for this specific model system is missing. And more details can be found on this paper. So to summarize, so this was the first experimental measurement for this kind of fermion quadrupling condensate. For this other kind, recently was published a paper where they observed some indication for this phase in this Kagome material, where they measured essentially this, they performed a little Parkes experiment, and they found that the oscillations changed from being h over 2e to h over 4e and 6e, suggesting even the presence of sextuplet condensate. But these experiments still need to be verified carefully, and so I'm just reporting it now. Instead, more interesting, and even recently, it was published. It was January 2025 that now it got published in Nature Physics. That the bosonic counterpart of this kind of condensate was realized in this two-component system, bosonic system, realized with these optical lattices, where these two components are singularly Mott insulators, but they have superfluidity in the counterflow. So just to conclude, I would like to present you our last investigation, if I have time, because we were essentially looking for other materials where this phase could be realized and seek. And we thought about the magic angle twisted delay graphene for two reasons. So essentially, it's a bidimensional, two-dimensional systems. It's known to break multiple symmetries. So it has the ingredient, it's multi-component most likely. So it has the ingredient we needed. The two-dimensionality also is important because, of course, phase fluctuations are more important. So we started from studying functional, that was Landau functional proposed in this work for Ralph Fielding, where in this paper they found that the principal pairing channel is this plus minus ID. I don't want to dig into it, just an excuse to study a model that can be relevant for other systems eventually. I know it's still very debated. So what we did has been to study essentially this functional, which can be rewritten essentially. These are the two components that can be rewritten as a function of two angles. One is the phase difference between the two condensates, and then this gamma account for the relative amplitude fluctuations, because you can, if you assume that the total density is constant, you can rewrite these two amplitudes in terms of sine and cosine of this gamma, and this is what you get. And the interesting thing of this model is that it has two different regimes. So depending on the sign of K, you can have either for K larger than 0, a ground state that is a superconductor breaking time reversal symmetry. And this is the case of this plus minus ID. But in principle, you can also investigate the other possibility, the other, let's say, pairing channel, where k is smaller than 0, and then you have to introduce also another term in the functional, where the ground state is a nematic superconducting ground state. So we are currently studying this phase, but today I will present you these results for this regime. So what we did, essentially, we studied this free energy by looking at the phase fluctuations of the two components, but also at the relative density fluctuations. So we also account for these degrees of freedom via Monte Carlo simulations. So we need to assess these two-phase transition, zeta-2 phase transition associated, sorry for this tiny thing, associated with the phase difference, so this chiral order parameter. And then we need to assess the BKT phase transition for the superconducting sector. Essentially, the game is to assess which of the possible topological excitation of the phase proliferates first. If it's the case of vortices, we can have first a BKT phase transition and later the zeta-2. If we proliferate first zeta-2 domain walls, it's the other way around. But in principle, we can also proliferate objects that are composite, which are formed by fractional vortices and these domain walls between the two possible chiralities of the two components. And if they are the first proliferating, then we will have a single first order phase transition. Let me point out again that stabilizing this fermion quadruplets phase is not trivial, actually, because if you do the calculation properly and if you account properly for the interaction between different topological defects, very often is the case that the proliferation of one object triggers the proliferation of the other topological defect, and you end up having a first order phase transition and not splitting between the two phases. And this was the case of many other models where this was investigated. In our case, what we found is the following. So we assessed the zeta-2 phase transition by defining an Ising parameter for the two chiralities and by computing the Binder cumulant. For the LCD, for the BKT phase transition, we look at the superfluid stiffness with the BKT scaling associated with the phase sum. And these are the Monte Carlo results. So as you can see, for different linear size of the system, which is the way to extract the critical temperature. For this value of K, we could find quite clearly a separation between the two critical temperatures. So this is the BKT1, and this is the zeta-2 So essentially, in between these ordered phase and the disordered one, it appeared this fermion quadrupling condensate. Quite interestingly, if we we also looked at the different values of K, and we could always find a splitting between the two transitions, which is quite rare, even for very small value of this parameter. So this is the difference in TC, which is very small, but we also took a very simple model without any additional interaction and assuming extreme type 2 limit with no coupling with the electromagnetic field. So this suggested that differently from previous model, this model is very promising for observing and detecting these new phases. So maybe it is not a good model for merging angle twisted Bilay graphene, maybe yes, but it is worth to look at systems that can be well described by this model and see if one can observe a signature of this splitting. Yes, and yes, okay, there are still points that we are investigating. In particular, we want to understand better why, in this case, vortices proliferate always first than the other topological defect. And we also want to understand better the role of relative density fluctuations, which seems key in this case with respect to other models previously studied. And we are actually working on that via some ERG approach in collaboration with collaborators at ETH. Okay, before closing, I would like to acknowledge all the people involved in the many research lines I try to present very, very quickly. In particular, the last work has been done mainly in Stockholm with Egor Babev and Jan Karlström, and many experimental collaborators, in particular Vadim Grinenko. And also the previous work has been done mainly in Rome, but then it expanded with many other collaborations worldwide. And with this, I leave you with this conclusion that regards the last part, because it's where my research interests are focusing now. And with the new questions I would like to answer, in particular, I would like to understand how to tune and to engineer the emergence of these phases, since now we have the possibility to realize many two-dimensional crystal structures and to play around with orbitals, interaction, and stuff. One could think to realize, let's say, the optimal system where this phase could be observed. And in particular, it would be nice to understand how to tune also the emergence of this topological defect, and also explore more the new properties of this new phase of matter. And with this, I thank you for your attention.
So time for questions.
Good question. And thanks for the talk. It was very interesting. One is the superconductors you're studying are sensible to pair breaking effects due to many types of disorder. How will it change the formation of quadruple pairs? And the other one, you mentioned that if there are two competing superconducting transitions, typically you will have a first order transition between both, and that will prevent the existence of it. So is there a way when you have a system which tends to be unstable towards two superconducting phases to avoid that first order transition?
Thank you for the questions. So the first question was about quasi-particles. Of course, yes, there are these kind of fluctuations. So you can even see, I mean, already on the resistivity curve, you see that there is a region where you have this sort of Gisburg-Landau paraconductivity. So you have this pair breaking effect. But still, even in that case, if the pairs that are formed realize a condensate, this should be enough to observe some signature. Of course, one should take count of quasi-particles when looking to properties in transport and this kind of measurement for sure, and to see how they interact and scatters with this condensate. This is something that has not been explored so far, so it's a very interesting question. And about the first order phase transition, I think, so what I showed before was slightly different, but your question is still very interesting, so let me point it out here better. So essentially here, the idea is the following. So I have one superconducting phase transition and one transition which is this time reversal symmetry breaking one. So this chiral transition, if you like. Essentially, the idea is that very often you can have that the proliferation of, for instance, in this case, vortices immediately triggers domain walls. So as soon as vortices form, they very likely split apart in fractional vortices, and then you have no more room for these phases. When you have a transition from a superconductor to another superconductor, in the perspective of the fermion quadruplet, I can imagine it in maybe with respect to the charge 4e superconducting state, where you go from a superconducting state to another superconducting state. And then the nature of the phase transition depends on of course, on the dimensionality, and but it should be driven by phase fluctuations in any case. So let's say first order are typically, of course, typically when you have two broken symmetry in these cases, when two symmetries get spontaneously broken at the same time, and then you get this kind of signature.
Thanks for the talk. I learned a lot.
Thank you.
I have a question about the experiment you showed.
Yes.
With the evidence for this intermediate for fermion phase. I think the strongest evidence you had was this Nernst effect, which is a signature of breaking temperature subsymmetry, right? Which occurs, you have this peak there in the middle. Can this peak not be produced by some regular two fermion pairing, or a C-dagger-C pairing that breaks temperature subsymmetry, like loop currents, without signatures of superconductivity, or even a spin density wave, maybe?
So that's a very good question. I don't have it in the back as a backup slide, but they did measure, they did check via STM if some instability, of course, in some other channel, and it seems not to be the case. Also, there are not like magnetic impurities that could explain this signature, and also the fact that it really matched with this, specific heat and other signature, like in ultrasounds, you see that some modes that couple with the phase difference change slope exactly at that temperature. So there are, let's say, many evidence in this direction, but of course, we need, let's say, a smoking gun signature for this phase. And this also means that we need to think about an experiment that can really detect this phase directly without any source of doubt. But yes, so far all the measurements are consistent with this picture, and there are no reason to think about other sources. But yeah, it's a good point.
Can I ask another one? This is a more basic one, I guess. So the the U1 phase of a superconductor is by definition a symmetry in any system, right? You can without pairing, you can do this U1 transformation, and that's always a symmetry. The relative phase in, say, a two-pocket superconductor with two pairings, that's not really a fundamental symmetry. You can cook up terms that pin the relative phase.
Yes.
Like a Josephson coupling,
yes,
or some interband coupling, even without the attraction in superconducting. So this phase is not really spontaneously broken.
It depends on the system, and you're totally right. So in general, when you have, so in the toy model I show you, there was a huge missing term that was this Josephson coupling, right? That is typically there when you consider two-band superconductor or two components. So you have this term there that lock the phase. So there is no mode at all. So it's just a locking between the two phases. But for instance, for three bands is already different, because there you can really have this emergence of frustration, right? Or in unconventional superconducting state, like the one I studied for magic angle twisted beryllium graphene, where you don't have this Josephson coupling, because the two components belong to the same, if you want, band, so the same order parameter, and you have this B-quadratic Josephson term, which again lock the phase in these two possible chiralities. And in that case, this is, if you want, superfluid mode, but with discrete symmetry, which is zeta 2 or 3, depending on the model. But yes, it's not fundamental like the gauge symmetry.
Thanks.
Hi. Thanks for a nice talk. I just have very naive questions. First, for the superconductivity in twisted beryllium graphene, besides the D-type pairing, what did you take into account some microscopic model to describe the twisted beryllium graphene itself?
I can tell you how they did derive the model briefly. So they started the, I don't have an illustration for that, but so maybe it doesn't matter together. But in this paper here, what they did was to consider a patch model, so a 6-patch model around Ivanov singularities. And they actually did some ERG calculation to find which was the predominant pairing channel. And what they came out with was this pairing channel here. And once you know that this is the pairing channel, you can build up a functional, Landau functional that respect the 2-component nature of the superconducting pairing and the crystal symmetry of the system, which is in this case hexagonal. So essentially this was the, let's say, the procedure followed. So I just took what was derived as, if you want, Gisborne-Landau functional for coming from a microscopic model.
But then, can you, like in your calculation, can you see, like, for example, the length scale of the vortices compared to the molar length scale? Is it possible?
From my calculation, it's. I mean, I take it for granted. So it's not. I cannot see the molar structure. So
Thanks for the talk. So speaking about the smoking gun experiments, let's suppose that you could measure the short noise locally in your system. Would be this a sort of a smoking gun probe that you have a Cooper pairs of Cooper pairs, or would be not enough in terms of smoking gun?
So yeah, we are actually thinking about this kind of experiments. So to try to probe the phase in the end, the phase difference in this case. So for the charge 4E, of course, you can use the fact that the quantization of the flux change because it is still a superconducting stage though. So the problem of this fermion quadruplet superconducting, the one I presented, is that it's no longer superconducting. So it's not, it doesn't carry the properties of half quantization of the flux and so on and so forth. So you have to think about some other experiment that can couple with the phase difference rather with the phase sum, because the phase sum couple with the electromagnetic field, and then yes, you can do experiment to probe the fluctuation of the flux and then so on and so forth. But with this other kind is a bit more delicate, I would say.
Here's one really naive question from experimentalist. So I think that even in 3 dimensions, you have to have the phase coherence is established when Cooper pairs are overlapping. You have to have some finite overlap. But if the coupling is too strong, then the pairs are too small and they don't overlap, so there is no superconductivity. Is this the reason why you need two components? I mean, essentially, you could improve the establishment of phase coherence by combining 2 other parameters, one where the magnitude is strong and the other where it's small. So is this somehow related to your story to get these quadruplets?
In the picture I presented, so the Cooper pairs really formed and belong to different bands, and then they interact with each other. So the formation, yeah, of course, separately, if you like, in this picture, and then they try to establish a phase coherence overall. And this is done via, yeah, this interaction that can be Josephson-like or the standard.
But there is no need for one order parameter to be strong. And
no, there is no need. No, not necessary. This we also investigated this in the theory paper with Igor Babaev to see what happens if the density is different, but qualitatively is not doesn't change. So
So that's what. Thank you for the talk. I'm just curious. So how important is the symmetry that you propose for the final result? So would that work using a different symmetry or assuming a different symmetry of the
order parameter or the crystal? So it's something to be explored for sure, but I think one of the key things in this story is the fact that in this specific model, so this is my, let's say, gut feeling as a theoretician, is then when k is equal to 0, you are in a system that is fully symmetric, that doesn't have any phase transition, so the fluctuations are even stronger. And I think that somehow this proximity, so it is known, it was kind of known that if you increase this coupling strong enough, at the end, you stabilize the locking before the superconducting phase. But the fact that this is the case, even when k is small, I think is due to the proximity with this supersymmetric point. So let's say this b quadratic term comes, of course, from the symmetry of this order parameter. But yes, in principle, we are now investigating this case. For the nematic case, it's a bit more difficult to stabilize. What we are finding as a spoiler is that there is no splitting. So in this case,
so it's relevant.
it is. It's, yes, sorry. Yeah, it is.
So I guess that the story can be extended to more than two components.
Yeah, definitely.
Just get more complicated. But can you then expect, I don't know, 6?
Yeah, exactly. So the story about so this was already hypothesized for the pair density wave superconducting ground state. So in a system like Kagome superconductors, in principle, you can have 3 species, because you can have this pair density wave can be described in terms of 3 components. And then you can think about stabilizing this charge 6e, melting the order in the charge density sector somehow, so in the pair density sectors. So it's like this this picture that came from a paper from, sorry, too many animation when it comes to answer a question is a bit annoying. So it's like in this case, you see, so this is just for a simplest pair density wave order. And then essentially the game is here, if I melt first the order in this modulation of the pairs, I end up in this charge 4e phase. While if I first lose superconductivity, I just end up in a state that is a sort of charge density wave state before getting into the normal metal phase. But in principle, one can realize more complicated pair density wave structure and then end up in something that is 6e. And this is the idea behind the experimental paper of the Kagome material, where they observed this h/6e fluctuations suggesting the emergence of this phase. But of course, this can, there are also many harmonics that overlap, so it's not completely rule out the possibility that that is not the case actually. So when it's more experimental evidences. Yeah.
So if there is no more questions, maybe we'll wrap it up. Thank you, Ilaria, for a very nice talk.
Thank you.
And remember, there is another seminar in 10 minutes.